Okay, hello. Thank you all for coming to this session on social networks. We have an amazing set of 4 papers lined up for you today, so let's get started right away. My name is Kevin. I will be chairing this session. Each speaker will have 17 minutes for their presentation, followed by a 2-minute questions and answers session. And first, let's welcome Evan to tell us about seeding a simple contagion. Evan, the floor is yours.
All right, thank you so much for that introduction. Since our time is short, I'll just jump right to it. So this is a paper about targeting. All right, so imagine you're trying to sort of get something to spread, whether it be, get more people to participate in a microfinance program or share a piece of news or whatever. We often ask about, who we should be targeting. I mean, why are we asking this? Well, we know that peer influence is important for these kinds of, adoption choices. So, we might think that something about the network structure will help us, if we target the right people, that will sort of be more effective. Right, and so there's a lot of empirical work examining targeting strategies, largely based on various kinds of centrality measures. Um, but this work faces a number of challenges. So one key challenge is that data on networks in particular tend to be quite expensive and noisy to gather. So if you're a development economist trying to spread some new program or new agricultural technology, if you want to map the network, you're sending people on the ground door to door, surveying people about their social ties. You might not get everything. You might not get the most sort of important connections. On the other hand, if you're working at a tech company and you just have a bunch of data fall into your lab, well, still, I have a Facebook account with hundreds of friends that I haven't spoken to in a decade. So you might still have some data issues there. Now, even assuming perfect data, you might have this. We know that seeding problems are computationally hard, right? If you're trying to select exactly the optimal set of seeds, not really going to be feasible. You're going to be adopting some kind of heuristic method anyway. So, in light of these kinds of issues, there's been a recent conversation in economics about what is it really worth it, and a recent paper proposing in particular that at least in some cases it might be better to just invest in more seeds and distribute them randomly. Um, I'm gonna hope to convince you that we can shoot for something a little bit better, something in between. So what am I going to try to do? Well, I want to refocus our attention instead of thinking about centrality measures and targeting at the level of individuals. I want to think about grouping people into categories based on whatever demographics are easily observable, and targeting at that level. Okay, so gather some information on demographics, and then survey not everybody but a sample of people. And you don't need to ask just exactly who your friends are. Ask simpler questions, what are termed aggregated relational data. So things like, how many friends do you have, how many of them are men, how many of them are women, how many fall into some demographic category that I have data for. And so the approach is then to basically, group people into these demographic buckets based on the information you have on hand, um, estimate some network summary statistics for each bucket, and then you're going to pick a bucket or possibly, buckets and target randomly within those categories. Okay, so then the question is going to be, well, which bucket do I pick, and how much better am I going to do than random? So that's the subject of this paper. Right. So to give an overview, all right, so I'm going to study a simple SIR model. So, I think of this as a benchmark, not necessarily representative of, every, seeding problem you would care about, but I think it's an important building block for further work. And how am I going to use these summary statistics, the sort of data, aggregated relational data? Well, I'm going to use them to fit a random graph model. Okay, and this is going to be a model that has a, finite set of, types. These are the demographic buckets. And we're going to try to describe, type-dependent linking patterns. And once we have that in place, I'm going to, analytically solve for what I call a seed multiplier for each type. And the way you should think of this is, as long as, my seeding budget is pretty small, basically, what is the value of seeding one more individual of a given type? And what I mean by that is, if I seed one more person of that type, on average, how many more infections is that going to generate? Okay. So the main results then, we're going to obtain explicit formulas for computing seed multipliers, and this analysis breaks down cleanly into sort of two cases, what I call the non-viral and viral cases. So non-viral when sort of all of the components in the sort of resulting graph are small, in the viral case when there's a giant component. So I'll talk a little bit more about that later. And we're able to get a handle on some comparative statics and at least some of the qualitative features of what makes a good target. And so I'll make one sort of key distinction between the two cases in a few slides. The other sort of major part of this project is, really, I want to, people to think of this as, not just a theoretical exercise, but actually a tool that you can, take to the real world. And so I'm going to, run some simulations using the Indian village network data from the diffusion of microfinance paper. Okay, I won't belabor the related literature except to say that it's large and spans many fields. But as I already said, data and computational resources are, challenges sort of throughout this literature. And I really want to emphasize, again, where I think the sort of, conceptual contribution of this project is sort of refocusing our attention away from, targeting individuals, finding that, one, or a handful of, great seeds who might be, really sensitive to exactly what connections we have in our data, versus targeting at the level of these groups. Okay, now I do want to point out that there's a small recent literature in economics that sort of implementing similar ideas in sort of different application domains. So I'm taking this idea into the sort of targeted seeding setting. If I have time at the end, though it seems unlikely, I will hope to spend a little bit of time talking about the alternative benchmark of random targeting. Okay. Let me do a brief pause and see if there's any questions right now. Otherwise, I'm going to jump into the model. Okay. So I'll assume everybody's with me on the overview and just keep on going. So I'm going to cover things in three parts. I'll talk about the diffusion process, the network model, and then how seeding works. Okay, so I'm going to study, like I said, a very simple contagion process. We're going to have a large population of individuals linked in a graph. Each one belongs to a finite number of types, and so each if I have type T, then with probability alpha T, I'm susceptible to whatever it is that's spreading. If I'm susceptible and I get exposed, I get infected. If I get infected, I expose all of my neighbors. And so you can see quickly, this is a sort of standard cascade model. I expose neighbors, some of them get infected, they expose their neighbors, some of them get infected, and so on until the process burns itself out. What about the graph? So I'm going to represent the network using a multi-type configuration model, and I won't spend time on the technical details here, but you can obtain this as a limit of finite models. Intuitively, you should think of this as basically taking a uniform random draw among graphs that match a particular set of summary statistics. And if you take limits correctly, everything, the results I'm going to tell you are going to hold almost surely for the graph that is realized. Okay, so what are these summary statistics? The sort of data I want this to rely on. So okay, we have our finite set of types. There's some distribution of types in the population. We have for each type, they have a degree distribution. So, sort of how many friends do you have if you're a given type, and that can vary from type to type. And also each type has a neighbor type distribution. So I might be, for instance, more likely to be friends with people who are my own type. So you should think of, if I'm type T, each one of my neighbors has a type realized independently according to Z sub T. I want to impose just a little bit of consistency conditions. So I'm assuming an undirected graph. Okay, so I'm going to write PT for the fraction of agents who are type T, mu T for their average degree, and QTS for the fraction of their neighbors that have type S. And all this little equation means is that the number of links going from type T to type S has to equal the number of links going from type S to type T. Okay. So seeding. S sub T is the probability that a type T agent gets exposed sort of ex ante, so exogenously. All right, and so the seeded fraction is going to be P dot S. So remember, the entries of P are the sort of fraction of the population that is of each type. All right, pi sub T for the fraction of type T agents that eventually get infected after the contagion process has fully burned it, has fully gone through. And pi is the total fraction of the population that gets infected. Okay. And then the seed multiplier is the sort of values that I'm really interested in. So look, notice I'm taking a limit as the seed vector goes to 0. So this is, again, we're seeding a small portion of the population. This is sort of a normalized effect of seeding more of type T. So intuitively, what this represents, if I seed one more type T individual, beta T is the average number of infections that's going to generate when the seed vector S is very small. Does this make sense? Okay. Well, I can explain a lot of the sort of qualitative intuition of the model through a pair of pictures. So this is just a graph on a couple hundred nodes realized at random from an Erdos-Renyi model. So in both graphs, right, there's two types, the red type and the blue type, and the red type has twice as many neighbors on average as the blue type. Okay. And so if we're thinking about targeting at the level of types, the sort of obvious intuition is, well, red types have more neighbors. They're going to be in bigger components in the percolation graph. Obviously, you should seed them. All right, and if you look at the graph on the left, that's absolutely true. So if we assume everybody is susceptible, then you put a seed in there, you get everything that's in the connected component, right? And the red nodes, the tend to be in larger components than the blue nodes. So if you're going to drop a handful of seeds, on average, you're going to do better by seeding the red nodes. Okay, so that's not earth-shattering at all. Looking over on the right, though, something different is going to happen. So if the network is more dense, we're going to end up with this giant component, and that's that big component in sort of the middle bottom of the graph. And once I've thrown a few seeds in there at random, it's very unlikely that I'm going to miss the giant component. So even if I seed the low degree type, the blue type, I'm going to hit it. So what's the marginal impact of another seed? Well, it's going to depend on if I want sort of more impact, it's going to depend on whether I'm hitting these smaller components that are outside the giant component. And because basically all of the red nodes are already in the giant component, if I seed them, it's redundant. I'm not going to sort of get any additional benefit beyond the giant component that I'll hit within the first couple of seeds. So when the network gets sufficiently dense, it's actually going to be the case that you're better off targeting lower degree types. So this is just sort of an illustration, but this kind of intuition is actually quite robust. All right, and if there's only one thing you remember about the talk, that's what I want you to remember. Okay, so let me get into a little bit more detail with the model itself. So in the configuration model, one of the things that makes it analytically tractable is that it's locally tree-like, so I can compute outcomes using a simple recursion. So if you think about the graph, the sort of local neighborhood generated around a random player, it's as if you're generating a branching process. The first guy that you pick has a type drawn from T, degree drawn from D sub T. Each neighbor draws a type from Z sub T. But then as you're sort of going forward, every sort of branch that occurs afterwards, you have to do a couple of corrections to the degree distribution. You have to adjust for the friendship paradox, and you have to not double count the link through which that neighbor gets exposed. Okay, so this is what I call the forward distribution. So this is D prime sub S, the if I expose, or rather, if I infect a type S neighbor, how many additional neighbors are they going to have? And that's going to follow this distribution, where again, for the friendship paradox, I have the degree weighting, and to avoid double counting, there's the offset by 1. Okay, so as far as obtaining the formulas for the seed multipliers, let's get a little bit of intuition for how we can go about doing that. So if I expose a type T individual, how many new infections am I going to generate on average? Well, at sort of one step away, right? Think, well, I have mu T neighbors on average. A fraction QTS of them are type S, and a fraction alpha S of those are susceptible. So this little M sub T sub S, that's the average number of type S infections I'm going to cause at one step. Right? Now, if I'm a type T person who was just exposed by a friend, well, how many additional neighbors am I likely to have? Well, that on average, I'm going to have mu prime T additional neighbors. It's the forward distribution. Right, and so M prime sub TS captures, okay, how many additional type S infections am I going to cause now that I've been infected? Okay, so these, you can write these into a table. We get a couple of matrices, M and M prime. And when you think through this just a little bit, you realize, well, after sort of K steps of this contagion process, this expression on the first line should capture, how many infections on average seeding a type T person is going to generate. So it's alpha T out front because they have to be susceptible. If my seed isn't susceptible, I don't get anything. The 1, the first term inside the parentheses, is getting the seed itself. Then the term that is just dependent on M is 1 step of contagion. MM prime gives you 2 steps of contagion. M prime squared gives you 3 steps of contagion, and so on. And if you let the process go all the way through, it should converge to that expression intuitively. It converge to that expression on the second line. But notice this is only going to be well defined if the spectral radius of M prime is less than 1. Otherwise, this diverges. Okay, and so that's the case where the network is relatively sparse. Where in the non-viral case, there's no giant component, but everything works out that way. This sort of intuitive calculation is going to be a little bit more difficult to think through in the viral case. So if the spectral radius is larger than 1, the graph contains a giant component. Basically, we get that component almost for free. As long as we're seeding, a non-trivial number of individuals, we're going to hit the giant component. And the marginal impact is really going to be about the vertices that are not in the giant components. We're going to have to do some conditioning. But once we've done the appropriate conditioning, we actually end up with a formula that looks, for all intents and purposes, identical. It's just the mu and the mu prime are just going to, well, in fact, the q's and the alphas too are just going to be modified versions of themselves. Okay, so first theorem, in the non-viral case, the sort of intuition that we get just from this thought exercise is exactly right. The multipliers follow that formula. Now, I want to pause a minute and mention a few sort of nice implications of this. Notice that the entries of these matrices, M and M prime, are only dependent on the first 2 moments of the degree distribution. So, in principle, this, random graph structure, the contagion process, the exact details of it depend, on the entire degree distribution, on sort of fine features of the model. We can, in fact, compute the multipliers using very low dimensional network statistics. So I think of this as being, valuable from a practical standpoint. We can also think through some sort of comparative statics that are pretty immediate from this. So the forward degree is increasing in the variance of the degree distribution. Okay, this is due to selection via the friendship paradox. And so as a result, if a graph becomes sort of more centralized, think about like a mean preserving spread in the degree distribution. So you have some people with a lot of friends and more people with very few friends. You actually are going to have higher multipliers in that case. So these sort of very centralized graphs are much better at spreading. And like I alluded to on the
Evan?
last slide, yes.
Evan, you may want to wrap up because you're near the. We should switch to Q&A soon.
All right. Yeah. Okay. So maybe just quickly mention a little bit about the simulation. So, as a proof of concept, I simulate this contagion process on as I said, the village networks from the diffusion of microfinance paper. So we've got data for 75 villages, and once we've sort of restricted to individuals for which we have demographic data, there's sort of small graphs around 100 to 400 individuals per network. I'm going to estimate multipliers via simulation. So I'm going to basically fit the simplest model that I can, a two-type network with sort of men and women as my demographic buckets, and sort of compare the simulated multipliers from actually seeding a few men versus a few women to those that we compute based on the matrix formulas from the previous theorem. And skipping over some details, each dot in these plots is a village. So the left is multipliers for men, the right is multipliers for women. Basically, if all of the dots lined up on the 45-degree line, that would be sort of perfect fit model to simulations. It's obviously not perfect, but for all intents and purposes, I think this is pretty darn good. Since I'm out of time, I will not sort of get into the details there, but I'll just, I'm happy to address it more in questioning. So yeah, so just to wrap up, I think of this project as seeking, a middle path between sort of these kinds of extremes of targeting at the level of individuals and just throwing our hands up and targeting randomly. So I think that's a pretty important change in focus relative to the literature, and I think it may well offer a practical way to choose better seeds. Deals with sort of data limitations and computational constraints quite well, and at least in one set of simulations, it seems to do reasonably well, even in very small graphs for which the limit results. You might not expect them to be a very good approximation. All right, I'll go ahead and move on to questions then.
Thank you very much, Evan. Are there questions from? Thank you very much. Are there questions either from the room or from the virtual audience? Yes, please. In the back. You may have, you may have to come up here, or I can read. Evan, are you able to hear that question?
I cannot hear the question at all.
Okay, so the question is what is the connection of this between this work and the work on, let's say, seeding graphs with like a community structure, right? It's like stochastic block models.
Yeah. So you could think of at least in some ways a stochastic block model as being a special case here if your stochastic block model is sparse, right? So implicitly, as I'm taking the population size to infinity, I'm assuming expected degrees are bounded, right? So, if you, let things sort of scale up, you're going to end up with a graph that's, super, super well connected, and you won't need to do any careful targeting to get, to get things to spread. So I think you could view the stochastic block model in, a sparse stochastic block model as a special case where, the distribution of connections is a compound Poisson distribution.
Yeah. So the question here is, it seems like on denser networks, this multiplier would make sense. I mean, did you want to ask about the sparse one? Is the question about?
But I think of this as being especially relevant in sparse networks because if we're talking about a simple contagion process, if the network is very dense, there's basically nothing to be gained from targeting. You drop one seed in, everything's connected, everything gets infected, right? Targeting only matters if, well, I guess the sort of subgraph among susceptibles is sparse.
Thank you, Evan. I think in the interest of time, we should move on to the second speaker. And so we have. Thank you very much, Evan.
Thank you.